How to what? How to self-replicate in the lab. And you're going to tell us about how to do it otherwise. So, this isn't quite fair, I think, because in the United States and in Europe and a lot of the civilized world, it's illegal to schedule somebody to talk directly after Vladimir, right? Because his talks are so good. And especially if the talk is before cookies, right? So I'm under a double handicap, so I'll try and... I didn't schedule when I was talking. Oops. Okay. So, well, no, that's okay. you can, yeah, you can publish this, I guess. Okay, so a lot of soft matter and stuff, actually all of soft matter deals with materials that come from light. It's a little bit unfortunate that you can't do soft matter, in deep space or anything like that. The molecules and stuff we work with derive from light. The stuff that we're studying, active systems in this meeting, essentially all involve things that we look at, that we learn from living things. So I thought, well, if that's what we're about, if that's what soft matter is about, probably the hardest thing, the big challenge, would be to make our own life. So we don't have to mimic anything. We can have our own life to deal with. So what I want to talk about is artificial life and what we're trying to make artificial life. And it's very controversial. That is how you define what artificial life is. It's sort of straightforward for me. This is a replicant from the movie Blade Runner, right? And she's artificial life, and I want to make her. So that's what we're after. When you look in definitions, for definitions of what life is about, it is ill-defined. I mean, it's not defined what you're allowed to include in something that's living or what it's not. It's very controversial, just the idea of what is life. But there are sort of 4 ingredients that people tend to, or scientists tend to think of as associated with life. The ability to move, motility, a metabolism, a way of transforming chemical energy into other forms of energy. Those things are pretty straightforward, and as a matter of fact, Jeremy will describe what we're doing on that, and you've already heard Christina about what people have done in terms of converting, in terms of motility and metabolism, getting chemical energy to give you work. I think the real essence of the problem is self-replication, which in itself is ill-defined, because when you say self-replication, people tend to think, oh, I'm going to put something somewhere in space and it's going to double and then it's going to quadruple and stuff like that, independent of anything else. And nothing does that because it needs matter, it needs energy. We usually need a mate to do it, right? And all sorts of, we need, amino acids from other sources. So you don't usually do this alone. But what I'm going to tell you about is experiments we were doing. The first experiments were, a couple of years ago, where we made an artificial system where what we could do is make a seed and put it in a bath, and we get a copy of it. And in this time over here, we essentially made 3 generations, parents, daughters, granddaughters, like that. Then it turned out it was pretty, what we were doing was very clumsy. I guess that's not quite the right word. But in any event, it wasn't as elegant as we wanted, so we changed the system to a system which we now have, which is what I'm going to describe to you, which works simply by taking a seed, putting it in a bath of particles, okay? You cool it down, okay? It organizes the particles, the complementary particles on top of the seed. You then shine on light. It's not me, I don't think. Okay, yeah, you shine on light. It cross-links them. You heat it up, and you have a copy. You cool it down. You shine on light. You heat it up. You've got 4 copies. And it grows like this. And it grows exponentially. And so far, what we've done with this is we have something like 24 generations. Okay? 24 generations means we've taken our seed and we've replicated it so we have something like 7, 8 million offspring from that. And we could go on forever with that. Once you have evolution, once you have exponential growth, a natural thing that you might think of doing with that is doing evolution, seeing whether you can get evolution from it, which is one of the other things you usually associate with living systems. And I thought that would take some time, but essentially we have a system. Our original system we've already gotten so that we can selectively change the growth of one species relative to the other and have it take over the system. And I may as well sort of show you that in a second. One of the reasons I was doing this is just to upset all my friends who do biology, because my freshman physics teacher over here has on his blackboard, what I cannot create, I do not understand. So if you want to understand biology, you have to be able to create it. And that's sort of one of the objects of this. Okay, so I'm going to tell you the end of what we did, and I'll tell you how we got there. Basically what we did is we took a set of tiles. These are actually DNA origamis, which I'll tell you about. They have sticky ends. Their sticky ends stick down like that. They stick up like that on a complementary tile, and they also go horizontally. Okay? Now, these guys, these seeds that we put in, will arrange the A's, which are complementary, underneath them like this. When you cool down, you attach one to the other. They recognize one another. Okay, if at this stage you heat it up, okay, everything just comes apart and you haven't done anything. But if at this stage, when they're held together, you shine on UV light, okay, it will cross-link these guys over here, okay, and now when you heat it up, you get T's and A's, and that's what's shown over here. These are AFM images. There's the seed. The seed, you can actually write its identity on it. This is an A tile. These are two T tiles put together, and here's the T cells and the A cells afterwards. And this shows cycles where you go 2, 4, 8, 16. Now we could keep on going, but we need lots of tiles. So what we do is we go to 16, we dilute it by a factor of 16, we start it growing again, 16, 16, 24 generations, over 7 million copies. So that's the exponential growth, and it's really exponential. Now it turns out it's not exactly a factor of 2. At the end of the day, if you do 24 cycles with imagining you double each cycle, you get to something like 16 million. It's not so bad though. It's 1.97 instead of 2 per cycle, which is pretty good. Okay. Now with those, what we've done is after we have these guys growing, we made us 2 sets of them. One has a red dye in it and one has a green dye in it. This cool down step over here, where you cool the system down, okay, and the A's associated with the T's, okay, depends on them getting cold enough. And if you put a dye on this and you shine a red light on it, this one remains a little bit hotter than this one, okay? And so you've changed, this thing still grows, but it grows slower than these guys do. And after 6 cycles, well, if you don't shine any light on, okay, there's no distinction between these 2 guys. You make a 50-50 mixture. After 6 generations, they're essentially 50-50. If you shine on a red light, then the green guys are better because they get colder, they don't get hot, and they take over and they're 95% of the system, and the other guys, these guys, the red ones, are only 5% of the system, and if you switch the light, it's the other way, okay? And that means that we can select, just like nature selects, okay, the system, the species, okay, which can grow fastest. And you can use this supposedly to do evolution toward a trait that you want. This is the start of it. Now, one of the things that I'll show you, which is actually very cool about this system, which actually wasn't an accident, it was designed to do this, okay, is you might say, this actually is complete nonsense. What the hell does this have to do with self-replication? okay? I'm changing temperature, I'm cooling it down, I'm heating it up, I'm shining on light, da-da-da, right? But, okay, the sun does that every day. And so one of the things you can imagine is you could take this outside and just leave it outside. And we did that on my rooftop a month ago, and it works. So this stuff, where you cool down, okay, it had to be so it's cold enough at night, right? You had to do it so when the sun comes up, it hits the sample, okay, and only for a certain amount of time, okay, but it worked, okay? At least it worked a couple times, okay? We haven't gotten it to take over the world yet, but we'll see. Okay, so that's what I'm going to tell you about. And here are the people that have been working on it. It's mostly the group from soft matter at NYU and from chemistry at NYU. I'll talk more about this guy. This guy's sitting over there, okay, and he contributed to it. And lots of really good people. Xiaojin is the one that finally got the whole thing to work at the end, which is really cool. So let me tell you, where's the clock so I can keep track? Don't go too far over. So the basic idea is this. If you want to do self-replication, at least the way I've been thinking about it, which I think is the simplest way I can imagine, is you need two elements to it. You need specific reversible interactions, and you need irreversible interactions. You want to make something that stays from one generation to the next. The way you get specific reversible interactions is, in the easiest way, you could do this by inventing your own chemistry, inventing your own, making certain physical interactions, okay? You could probably even make specific depletion interactions like we heard in the last talk by making shaped particles, and we did that as well. But the easiest way to do it is use DNA, because DNA, as you all know, okay, you take a strand of DNA with certain bases on it, and it will bind only to its complementary strand, and it'll bind strongly to it, right? And moreover, it's reversible, because if you heat that up, it comes apart. And you cool it down, and it comes together, and it associates with a specific partner. Okay, now that's not really the reason I did it. The real reason that we did it this way, this is supposed to show a colloidal particle with a double helix of DNA on it, and then a sequence over here, which won't stick to itself, but will stick to a complementary sequence, which is on another colloid. And the reason I did this is because I have buddies who told me it's easy, okay? And I'll tell you why it's easy. It sounds like it's easy because I just told you the complementarity. That's not the real reason it's easy. The real reason is you can get colloidal particles, okay, with streptavidin on them. This is a protein, okay? You can get that from like 4 or 5 different companies, right? You just buy it. Streptavidin binds biotin to it in an almost covalent bond, a strong bond anyway. And you can buy from maybe now at least a dozen companies. This one is IDT. DNA, any sequence up to 100 letters, okay, attached to a spacer, attached to biotin for $60 for 100 nanometers. No, nanomoles in this case, right? For 100 nanomoles with guaranteed overnight delivery, which takes about a week, okay? Nonetheless, it shows up really quickly, and you just design the strands, okay? Now, you think, okay, this is okay, but I still have to figure out, if I've got a sequence GTCA like that, what the interaction energy is, what the enthalpy is, what the entropy is, what kind of temperature and melt and stuff like that. Nope. You go to the web, and you find a bunch of websites where you type in the sequence, and it gives you the melting temperature and the thermodynamics. And this is all done because DNA is important, because we've got DNA in us, and people want to know what's in them. And so there's been decades and decades of work on DNA. Okay, and all of this makes it really easy. The other thing that makes it really easy is across the street at NYU is Ned Seaman. Ned Seaman invented this whole area of DNA nanotechnology. DNA is not really the secret of life. He's the first guy that realized that you could use DNA as a functional material. You could make things with it. And he made all sorts of things with it. He made crystals from it. He made Boranian rings. I forget, I can never pronounce it right. What? Boramain rings, okay. No? Boramain, okay. He's done all sorts of stuff with it, and he's across the street, and this work is all in collaboration with his group. People have done stuff with it before. They took nanoparticles with DNA, and when gold nanoparticles get together, they turn blue. Chad Merkin did this. He uses it as an immunoassay to test for RNA, to test for expressions and things like that, and diseases. And Crocker and us and Pine and other people all started showing you could do this with colloids. Now, the only problem with this is, to scale, what happens is the colloidal particle looks like that, and the DNA looks to scale like this. And there are lots and lots. It's not like there's one DNA per particle. There are typically like 10 to the 4th or 10 to the 5th DNA strands per particle. And it turns out, although this is easy, the thing that people didn't tell me, partly because they're biologists and biologists speak a different language than physicists do, this doesn't always work. And then I learned the following, which is that when a biologist tells you something works, they mean that, you know, it works sometimes. And if you're lucky, what they mean is that it works often. But they don't mean that it works always, which is what a physicist means. And the reason for that is obvious, because it doesn't have to. You have redundancy built tremendously into any biological system. So if one thing doesn't work, something else will take its place. It doesn't have to work all the time. And so what would happen, for instance, is the DNA very nicely has a hydrophobic part, doesn't like to be in water. That's the oily part, that's where your bases are. And that guy, if you can find the plastic surface of one of your colloids, it will stick happily to it, and it won't care what it's covered with. So you have to find a way around that, and that, it turns out, is something biologists know very well. The problem is not specific interactions, it's preventing everything else from happening, right? All the non-specific interactions. So the simple answer in this case was to put a polymer brush on the surface, which is about the same height as the DNA, okay? And then you only have the sticky ends of the DNA sticking up, and another particle won't have its DNA find the surface. It'll only find the sticky ends. Once you do that, you can start doing science with it. These are just aggregation and melting curves as you heat and cool the system. This is temperature time. You see they aggregate, and then they melt, and it's repeatable time and time again. So now you can start doing stuff with it. So now we're going to do self-replication. So you start looking at papers on self-replication to see what other people have done before. I love this paper. Actually, I love everything that Penrose's did. You guys know Penrose, right? Penrose is Penrose Tiles. He's, what's his name's advisor? Hawking's advisor. He's done all sorts of stuff in cosmology and stuff like that. This isn't him. This is his father. His father was a chess grandmaster and stuff like that. But these guys are incredible guys. They're sitting down one evening talking together. He says here in this paper, it happened that my colleague Roger, okay, mentioned that, his colleague Roger, his son, Roger Penrose that we know, maybe 12, 14 years old at this time, right? And they decide they're going to figure out self-replication. So what they say is, well, this is pretty easy. What we'll do is we'll take a bunch of sliders and put it on a trough, and we'll rock them back and forth like this, right? And these sliders have on them these bumpers, so when you slide it back and forth, they just bump into one another, they don't do anything. But if you hook two of them together like this, then when you slide it this way, it latches them all up, right? And you slide it back and they're all latched together, okay? So that's pretty cool already. But these guys are very smart. They said, well, that's crystallization. And crystallization is not self-replication. Crystallization is a process which usually grows algebraically, okay? It doesn't grow exponentially. And moreover, it's not so useful because if you have a defect in a crystal, it usually doesn't copy, right? If you make a crystal from that, it's not going to copy. They also said, however, that if you want it to grow exponentially, you can do the following. You let the crystal grow for 20 minutes, and after 20 minutes, you can take a hammer, and you can smash the crystal, and now you get lots of little crystals. You let them grow. 20 minutes later, you smash all of them, and let them grow, okay. But that's not very, I think that's not a good way of doing it. Some people are actually trying that with DNA, stuff like that, growing crystals and slicing them and stuff. But they realized this, and that's something worth remembering. Then they went on and they made sliders where they don't grow crystals, they just replicate themselves. And they said you can only do two this way, so we're going to stack them up sideways. So we can have, instead of only two different species, we can have, 2 to the n species we're in, is how thick we made this. And this is a Nature paper where they actually made these guys and showed that you slide them together and they latch up and they can self-replicate. It's really neat. They've done amazing things. I'm not going to do it that way. I don't want to build sliders. We want to get, millions, billions, 10 to the 12th of them, essentially. And I don't want to build these little models 10 to the 12th of them. That's kind of hard. Okay. So here's the scheme that we're going to use. We take a seed. Okay. The seed is going to have, in this case, a 2-letter alphabet. The information's in the sequence in the seed. So A, B, A, B, B, A is different from A, B, A, A, A. So that'll be distinguished for us what's going on. I'm going to link them permanently, and they're going to have sticky ends. And I remind you, this isn't one sticky end. This isn't one DNA up. It's, tens of thousands of them. Okay. Now I'm going to put this in a bath, and the idea is it will assemble the complementary colloids, okay, on top of it like that in the right sequence, and they're bound like that. And now I've made a copy. But if I just heat this thing up, it all comes apart. So what I have to do now is find a way to, when I shine on UV, cross-link these guys. And if I can cross-link these guys so they're permanently linked, when I heat it up now, I have a copy, and I double my number, and I can keep on going like that. That's the idea. Making the seeds is easy. You just take laser tweezers, and you put them together. That's, for instance, a possible seed, which is its own colloidal particle, because we've linked them together with this UV linker. Okay, so I'll skip a lot of this stuff, keeping track of time. So here's the idea. How do you get this to work? So first, just going from A to A prime and B to B prime, I just use the sequence, a specific sequence of bases in my DNA on A, and the complementary sequence on A prime. Okay, A goes to T, G goes to C, etc. Okay, and I have a separate sequence that makes sure that B goes to B prime. Now, the problem I have over here with linking them, so it's easy to get this. It's harder getting this because I don't know what I want to link to what. Sometimes if my seed, okay, has B next to B over here, sometimes I want this to link from B prime to B prime. Sometimes I want to link from B prime to A prime. So I have to make this general, okay? And the idea that we came away to do this was to use palindromes. So, and palindromes are well known in DNA. So you guys know what a palindrome is, right? They have that in Portuguese, in Brazilian too, right? A letter spelled one way, and it's the same thing spelled the other way, right? There are palindromes. It's much harder when I give this talk in China, right? Because they can't really do that. But in any event, so you make a palindrome, and it can go either way, and then, so it can stick to its, can stick to itself, can stick to the neighbor, can stick to whatever. So you put palindromes, B prime, you put prime palindromes on all of these, you're going to have different palindromes, unprimed palindromes on these, so the palindromes here don't talk to that. That's the idea. And now what you do is in the middle of these, you want something so that when these guys are held together, when you shine UV on it, it cross-links. That was something that we had to do new. But luckily, we have a really clever chemist across the street, Marcus Beck. He said, use cinnamon oil, and what he meant by using cinnamon oil is there's a compound in cinnamon oil called cinnamate, and cinnamate is well known to polymer chemists that you put two of these guys together, okay, like that, separately. You put this one, bind it to whatever you want, that bind to whatever you want. You shine UV on it, and it does a cycloaddition reaction, which covalently binds these two guys together, either in this configuration or that configuration. So what Marcus did is he attached this cinnamate molecule, okay, to phosphoramidite, which goes in the DNA backbone. So it just looks like this. You have your regular bases that way, and over here, sitting next to one another, you design your sequence so you've got these two cinnamate molecules, okay? And when you shine UV on that, they cross-link, and that's what should happen. Okay. Okay. To prove this thing worked, we wanted to figure out whether this really worked. So we did a slightly different construct of this, which is also something to do with assembly, I guess. We took a gold surface, we put DNA on it, we put a sticky end with a cinnamate over here. We had a complementary strand with the cinnamate next to it, a linker strand over here, which would go to a particle or anything else we wanted. You take the gold surface, you put this strand down on it, and you cover the surface. Okay? It sticks to the surface. You take the linker strand over here, you put it in, it attaches to the surface everywhere. You shine on UV in this region, you heat it up and you wash it out, and these sticky ends are then only where you shine the light, and now you can come in and that region is functionalized for whatever you want. So naturally what you do is you write NYU and you stick colloidal particles to it, right? And then you write NYU and you stick some dye on it, okay, attached to the colloid. And then you can see that it's a sticky patch, but when you heat that guy up, it just dissolves, right? Because you're heating up, you've got this permanently functionalized dye, and the hybridization to it is reversible with temperature, but that isn't. You send it to Nature Materials. Nature Materials says, well, this isn't good enough. You have to show us that you can do it with several different species. So, okay, so you make nature in red and materials in green, okay? Because you can functionalize this one way and this one another way, okay? And then you say, but we really want it on the cover of Nature Materials. So we're gonna write Nature Materials. And they write back and they say, well, you can't do that because although the font we use, okay, is Times New Roman, the letter A that we use is copyrighted by Nature, and you can't use it. So if you write Nature Materials with a regular A and not our A, forget it. Okay, so it is in Nature Materials, but not on the cover. For those of you who want to know. Okay. The physics of this stuff is kind of neat, of DNA attachments. That just showed you that the cinnamate works, essentially. But the attachments are kind of neat. So usually in physics, what I grew up thinking about, because I was doing hard condensed matter physics, is that a binding energy was a binding energy. And if you had some things bound with a certain energy, okay, then the only characters, then at low temperature, they're bound by the energy. It takes that energy to take them apart. At high temperature, you have to get to a temperature comparable to that energy to dissociate them. But when you're dealing with polymers or DNA, it's different because every time I hybridize a base with this complementary base, I gain some energy. But on the other hand, I start out with these guys being polymers, so they have entropy, okay? And when I bind them together like this, when I go from something floppy like that, okay, to something that's straight like that, I've lost a lot of entropy. And the entropy increases with the length, okay? So that I lose something proportional to the length when I bind the DNA strands. I gain something proportional to the length as well. So those two effects don't cancel one another out. And instead what I have to do is I have to consider a binding free energy, which is the energy, the enthalpy from the attractive interactions minus temperature times the entropy I've lost by hybridizing them. What is cool about this, and by the way makes your life exist, that is you wouldn't be living if there wasn't this effect, it means that at some temperature the binding energy of my DNA strands is 0. It's actually repulsive. They don't want to bind, right? And at some other temperature lower than that, I can be bound, and I can be bound so strongly that at that temperature, I will never come apart. I can be bound by hundreds of kT. And I can do that just by changing temperature, right? So temperature doesn't sort of boil you off, it sort of destroys your interactions in this case. And that essentially means that if I measure a melting curve, instead of being a width that's comparable to the temperature I'm at, it's a width that's much sharper than the temperature I'm at. This melting curve is usually, you imagine, two strands, okay, which you're going to hybridize to give you a single double helix. And you look at the number of single strands in your system, and the number of single strands reduces to 0 as you go through this melting temperature and everything hybridizes. Now you can generalize this to the colloids. Okay? You take the colloids, and they have many interactions on the surface. You can just write a partition function for each guy, which involves the free energy for them binding and the number of neighbors. And this is straightforward thermodynamics, so it's not interesting. You do this, and it fits the melting temperature between colloids now. These are colloids aggregating very well. That's not so interesting. It's a trivial calculation. What's interesting is you now have a melting temperature. You go from unbound particles to bound particles, and the width of this transition is a ½ degree. So you can make it so that you turn this interaction on and off if you like the temperature. It's very sharp. Okay. You can also figure out the kinetics of it. I won't do that. You can put many different DNAs on a particular particle. It's not quite as many as you think, because you have to make sure that if I have a word that's, let's say, 10 letters long, that 5 of the letters here don't agree with 5 of the letters that I don't want it to bind to, because then it will bind with some probability. And you want the probability essentially to be 0 at any temperature above the freezing of water. So you can typically get something like, take a particle and put something like 50, and then if you make it bigger, up to a couple hundred strands on it. I won't go through this. Okay, so everything was great. We were set to do this experiment. We were going to replicate the colloids. We got the colloids. We put them together. We bound the daughters on top of the parents like that, and we heated it up. For one thing, they sediment, so you only have 2 sides. And if they do both sides, that just gives you 2 daughters instead of 1, which is good, right? Okay, but it's going to be a problem we'll solve another way, as you'll see. Okay, because that's true. Otherwise, they're symmetric. That wasn't the problem we had. The problem we had is they wouldn't come apart. And so I was thinking, oh, something's wrong with the cinnamate. Somehow it's binding the wrong way. It's not great and stuff like that. But I had a graduate student, Lang Feng, who was much, much smarter than me. And he said, no, that's not what's going on. The problem is using palindromes, and palindromes not only stick to the particles they're supposed to stick to, they stick to themselves. So this is what we want to happen. We want to have a particle P1 to bind with another particle P2. But on the surface, since these are complementary, they'll also form loops. Now that shouldn't be any problem, okay? Because my other guy doesn't talk to this. My other strand has on a palindrome which doesn't talk to this, so it's not going to bind to it. And who cares if it loops, except if, when we're holding them together, it forms these loops, and they concatenate. And if they concatenate like that, then it doesn't come apart. And that was really cool. And unfortunately, we'd already gone on after this, because there are a couple easy ways out of it. That's Lang. One way is you can go back to biology. Biology has this problem of DNA entangling all the time. Whenever your cells replicate, whenever you replicate your DNA, it's got this absolutely magic enzyme. I have no idea how this works. This is absolute magic. Okay? What it does is it takes double-stranded DNA, it grabs one strand, it opens it up, it takes it outside and puts it together. Right? Absolutely amazing. So here's the first use of that outside of biology that I know. Okay? Here are our colloids stuck together. The black ones have one palindrome, the white ones have another palindrome. Occasionally they stick together like that, and now when you add topoisomerase, you see the ones that are stuck together, this doesn't come apart, that doesn't come apart, but the link between them comes apart, right? So you've actually opened these pairs. So we could do it that way, but we moved on. I should move on. I'm going to get to DNA tiles. This is what Ned does for a living. Ned Seaman, our collaborator, has done this for ages. Here is a simple structure that he makes. You take DNA, you take it over here, you leave a sticky end, you wind it around like that, like that. You take another DNA, you wind it around like that, take another one, wind it around like that. You have a rigid triangle now, okay, with sticky ends, okay? What can you do with that? Well, what he did with it is he made a slightly larger version like this, okay, with just little double two base sticky ends on the side, and he grew a crystal of it. Now, when you talk to people that do colloid science, when they see a crystal, they say, oh, that's great, you grew a crystal. And it's sort of, 10 by 10 by 10 if you're lucky, right? Maybe a real heroic effort will give you 20 by 20 by 20 colloids in a crystal. This is made from DNA on a nanoscale. These are crystals which are faceted, which you can see with your eyes, fraction of a millimeter, okay? They've got 10 to the 14th unit cells in them. And they're completely made from DNA and completely designed, okay? And one of the reasons that this is really exciting, and which is one reason why Ned will probably get the Nobel Prize for this, is because lots of people spend their time crystallizing proteins. You can stick a protein in there, and you don't have to crystallize the protein anymore. You crystallize the cage that the protein's in. And that's really cool. Anyway, Ned's a wizard at this stuff. Here's what we were going to do before. What we were going to do before is take our colloids and put them together. Now what we're going to do is we're going to take DNA tiles and put the DNA tiles together, and everything else should be pretty much the same. The DNA tiles are sort of complicated. They're little rafts made from three double strands of DNA. They have sticky ends sticking up like that. They have sticky ends sticking out on the corner. They have hairpins on them so you can read them with an AFM. Okay, so you can distinguish one from the other. The assembly of the seeds is actually complicated here. You design the DNA. The DNA self-assembles into different of these rafts. The rafts self-assemble into this larger structure, okay? You label it and you read it under an AFM, and these bumps indicate where these red tiles are, the B tiles are. You take these, you stick them into a bath of tiles which won't self-assemble, which can be assembled any way they want, and are organized by the seed that you put in. You cross-link them here chemically, which is why it was so clumsy this way. You separate them, you take them out, you look at them, and this is what you're supposed to see. You're supposed to see now they're labeled. The green ones are labeled like that, and you read them off, and you see that you made copies. In this case, it was like a 60% yield. But it was very clumsy, so you're not going to do this time and time again. It was really hard doing it. But this was sort of the first arbitrary system where you could design it and get self-replication. Okay? So the competition for this in the world of self-replication was people who were working on the origin of life. They want to know whether you can get RNA, which is supposed to be around before DNA was, and you can get it to self-replicate. So Joyce, who's worked on this for a long time, and Lincoln, took a ribozyme, which is a RNA enzyme, okay, which looks like this, and is made to stitch RNA together. And what they did is they cut it in two over here, and then they took the two pieces A and B, and if A and B came together, A and B would catalyze A and B, and it would self-replicate, okay? So we thought, okay, let's go to the simpler system. Let's use just two tiles, okay, and see how that grows. So here's what we did. We're doing it with origamis, but the idea was pretty much the same, except for two tiles. Okay, so an origami is a viral DNA about 7,000 bases long, And this guy, Paul Rothman, had a really cool idea. He said, well, I know the sequence. This thing has been sequenced like crazy. I will just take the sequence that I know, add little pieces of DNA. These are like 200 bases. Well, they can be 100. They can be from 50 to something like 200. Maybe 250 of them. And this one DNA linker over there will bind over here and will bind over there. So it'll fold this, right? Like you'd fold an origami. And you stick them together like that, okay? And it makes your structure. And so what Rothman did, okay, is he made all of these things, but this one, which is a happy face, got on the cover of Nature, right? That's why he made it, essentially. Yes?
So everything you're showing us so far from the assembly is assembly of structure. How about the mechanics of it? Can you make things, two joints that rotate around each other? Can you take two of these plates and have them flexible?
Yes, indeed, easily. What you do, it turns out, is, and you can make it as rigid or as non as you want. So you've got the DNA, which isn't as good as microtubules. It's got a persistence length of 50 nanometers, okay? So it's got a persistence length of 50 nanometers, and it's sort of rigid. You can hinge on that, but if you nick it, where you nick it, you add in one extra base. So now you've got two bases on a single strand coupling those. The persistence length of single-stranded DNA is up for grabs, but maximum 2 nanometers. Okay? Might be a fraction of a nanometer, right? And it'll pivot. It can pivot and it can bend.
So you could program a membrane with given connectivity?
Yes, you can program a membrane with given connectivity. Yes. Well, but I mean, this thing will still be fairly rigid because I don't think they've left any single strand, any non-double strands there.
Are the black dots holes in it? Is it a mesh or a compact? Yeah, here you've got usually holes.
Yeah, those are holes. But this structure is going to have the rigidity of the DNA in it. If I wanted to make this more flexible, like I wanted to make the mouth wag, what I would do is over here, where the mouth joins the top, I would have single-stranded DNA, so this is just loosely jointed and could easily go up or down, right?
So thermal fluctuations
The thermal fluctuations will move this thing. That's true. I mean, especially if I make it single-jointed. But this thing is pretty rigid, right? As it is. It certainly flops, right? But what you have to remember is, if, for instance, I ask how floppy it is from there to there, okay? Actually, this one is easy. This one is essentially, if I want to flop it, if I want to take that and flop it like this, the persistence length is 50 nanometers times the number of double strands I have in the cross-section, right? So if I have 50 double strands that way, okay, I'm a couple microns, right, in persistence length. If I make them too thick, okay, then you've got the R cubed going for you, or your thickness cubed going for you in terms of rigidity, and you can make it very, very rigid. Right?
Then, of course, I mean, there's a softness that arises from the coordination you're acting, which is not dependent on the strength of the individual components, but how connected they are.
Yes,
There
yes,
is a soft
yes.
mode that allows go like crazy.
Yeah. But you can over constrain it, right? You can do lots of things with this. I won't show that. Okay, but you know, so it's nice to be able to make these shapes and to talk about the connectivity and the rigidity and stuff like that. That's not why these are interesting. The reason these are interesting is you've built yourself a structure. It could be a smiley face, it could be a rectangle, right? And this is what we built. We built a rectangle like that. Okay. Let me blow it up. Here's what it looks like. Here's the strand from the virus. That's the blue. Here are the staple strands you put in to hold it together. You know on this object to within a nanometer where every single point is, and you can address it. What you can do is, instead of, if I want to address this point over here, Okay? Suppose I want to stick a gold nanoparticle there, or a DNA, or a fluorophore, or anything else. What I do is I just take this and I extend that DNA strand up out of the plane, and I know at that position exactly what I've got and exactly how to bind to it. So it's like creating a city, right? And labeling the streets and labeling addresses and saying, now I can put in those buildings anything I want. I know the address and I can get to it easily, right? That's what's really powerful about these guys. Really powerful. So you can imagine doing all sorts of things with them. Xiaojin is the one that did all the rest of the work I'm going to tell you about. Magician in the lab, fantastic to have around. So here's what we did. We took the origamis. We labeled a T and an A, right, like that. We're going to stick them together. These are made so that these sticky ends from the T attach to the sticky ends from the A, which are pointing down here, but are going to assemble on top or upside down. Okay, so here's what I showed you at the beginning. So we're going to take C's like that. They're going to bind A's. I think it's shown better. Oops, what did I do? That shouldn't happen. Okay. Yep. Here we go. Oh, this is kind of cool. Just to give you an idea. To read the T over here, what you do is you put a hairpin that looks like that. That is a DNA strand which folds on itself, attached to a staple strand, and the staple strand goes in over here, which means it goes in over there. That's your staple. This comes up from it. That's what, and now you put them in the form of a T on that, and now with your AFM you can read it, right? That's an example of what you can do. Okay? The cross-linking is done, again, actually in this case not with cinnamate, with another molecule. So we're going to take these tiles, put them together, and then in the region where we hold them together like that, we have a cross-linker, okay, which when you shine on UV, it attaches them together. In this case, it attaches a thymine base to this, this photo cross-linker. Seed is going to hold the A's together in the cross-linker. Well, here's the main thing. You start out with seeds. You hybridize the seeds together to make a permanent bond. This you have to do to start. Maybe you have to do it to start. We did it to start. You make the T's like that. You put the T's in a system which have A tiles and T tiles in them, randomly. Okay? These guys will assemble the A's when you cool them down like that. You shine on the UV, they're cross-linked. You heat it up, the T goes back into the cycle. The A goes into a cycle over here, where the A's, which are permanently cross-linked, now join the T's together. You cross-link them with UV, you separate them, and you get T's and A's. And in theory, this should double every cycle. Okay? So,
you cannot bridge T and A from the side, right? Only T and A like that, not like that.
no, you can also, if you make a mistake, T and A will bind like that. Okay? But the trick of all this is these things are effectively catalysts for the following reason. The hybridization of DNA, or the association of everything, depends on the concentration in solution, right? So what you do is you make these tiles at such a low concentration that they will never come together and bind on their own in solution. But when you bring them down, so these guys don't come together by accident in solution. Actually, they do come together, okay? But they don't stay together long enough, okay, in order for them to bind over here so that when you shine UV on, it will cross-link them, okay? On the other hand, when I hold them on the T's, when I hold them rigidly in place, if I figure out the effective concentration, I've increased the concentration by about 8 orders of magnitude, right? So now I've gone from where they're above their melting temperature to where they're below their melting temperature for the hybridization. And that's what makes it work. So this should double each time. The first experiment we did, we went for 8. It went, these are cycles. So it went 2, 4, and then it sort of saturated. went for 16, it went 2, 4, 8, and then it saturated, went for 32, 2, 4, 8, 16, and then it's saturated. Essentially what happens is, once you use up half of your individual particles, they're competing with the daughters for rebinding, right? So it doesn't work so effectively anymore, right? Okay, but it is exponentially growing for the first time for an artificial system. You go for 1024, you get about 516, okay? And it's growing exponentially. So then you get tired of that. Well, first, the way you actually do this is you look with an AFM. This is why it's so tedious right now. You look for your single tiles and for your double tiles. And as you see, as you go through generations, the number of single tiles goes down until essentially at the end you have nothing but 2 tiles, but doublets, okay? And that's your signature that you're getting. So here's what I showed you at the beginning. Again, this is exponential growth, and here it's going through 24 cycles. Okay. And that works. And as I said, it's not quite a factor of 2, it's like 1.97. You can also do it by gel electrophoresis. So you can tell the difference between a dimer when 2 of them together and a monomer. And you start out with a bath with essentially all monomers, okay? And that's where the dimer band should be. You add a C to it, and you can see as the generations go down, you're converting monomers into dimers, and it's growing exponentially. That's just a check. Here's something that was cool, which is good and not good at the same time. So you do a control experiment. What's your control experiment? Don't put in the seed. If you don't put in the seed and you keep the same thing going, okay, nothing should happen. You should get no dimers. Well, in fact, you get some dimers, okay? But after 20 cycles where we would have gotten, if we had a seed, something like a probably 100,000 times magnification, here we get a 10% instead of 100,000, okay? So it shows you that, okay, you really need the seed. It's really what's going on. You're actually using the seed as a template, and you're growing exponentially. But occasionally you get these type of guys going together, right, by accident, right? And they're probably misformed, okay? Because what I was hoping for is the following. If you keep this going long enough, you expect it's sort of creeping up, creeping up, creeping up, and then it should go boom and take off. And if it goes boom and takes off, that's origin of life. Then you've gone from something that's not replicating to something that's self-replicating. And that would be the origin of life, at least in the lab, right? And that's what must have happened in nature, not necessarily with these materials, okay? But that's what should have happened in nature. So it's good that it didn't go haywire immediately. That would have been bad, but it's bad that it didn't go at all in terms of exponential growth. Okay, so now if we have exponential growth, what we want to do is we want to do evolution. So I don't understand evolution very much. The way I learned evolution was, you know, there were apes around. There's one species that's around that survives. It exponentially grows. You know, it's good. It takes over. Takes the environment. Okay, and then there's a mutation, okay? And the mutation, right, has sort of the same replication rate as the original species. And so with the environment the same and stuff like that, you know, Mark over here and, you know, the apes that he's, you know, they're in the environment, they grow at the same rate. And the ratio of apes to Marks stays the same. Okay? But then something happens. The world, for instance, might go from being a flat world to a round world. And now there's a big advantage now if you can figure out topological defects. And so there's a big advantage, okay, that the apes don't have, okay? And so Mark, with this tremendous advantage, takes over, right? And pretty soon there are a whole bunch of Marks around. And this is the way I understand evolution, right? Things grow at the same rate, okay, and then one of them has an advantage over the other because something in the environment changes, and you take over. So here's what we're going to do. We'll take our system, we'll dye it red, we'll make an artificial mutation, which is this one over here, which is dyed green. They should grow at the same rate until we change the environment. we change the environment in a very controlled manner this time. We just turn on a red light. The red light heats these guys. They don't condense on their parents as well, the individual components. So this guy will grow faster than that. The green ones will grow faster than red ones. If you change the light, the opposite would happen. And so that's just what's shown here. They're actually not red and green. They're both IR dyes, but they have different wavelengths. One is more toward the red than the other. There's a little bit of a trick here, which is actually something that's kind of cool to use for self-assembly and other things in activation anyway, which is water is a lousy thermal conductor. So in fact, if you shine light on something and it absorbs it, for instance, 1 microwatt on a 10 nanometer particle, if you absorb it, will raise the temperature there by 10 degrees. Okay? But the flow field, since you have to conserve heat flux, the heat current has to die like 1 over r squared from the thermal conductivity. That tells you that the temperature varies like 1 over r, which means that if you heat to 10 degrees in 10 nanometers, which you can easily do with 1 microwatt of power shining on the sky, 1 micron away, you're only 1 degree hotter. So you can locally heat the reds, and the greens are not going to get hot because they're about a micron away. And the size of these guys, of each of these tiles, is like 100 nanometers. So that's the trick that's used, okay? And here's what the experiment is. The experiment is, and this is one of the things I showed you also in the first slide, if you have apes and marks here, and there's no advantage to one or the other, their ratio stays the same, okay? And if you shine on the red light, which corresponds to these I guys, then the H's take over, and the I's decrease, and after 6 generations, you're a factor of 20 more of one than the other, okay? And if you reverse it, it's not quite as good, but almost, you're a factor of 10 over one than the other. Of course, if you wanted to, that just shows you that what we've done is we've changed the replication rate from essentially this was only 1.95. Well, that is reduced somewhat by the light anyway. 1.2 versus 1.95 gives you this profile, that way it is. You can also switch the lights in the middle and get them to reverse. Okay, how about growing it outside? So this is an experiment that a quasi-undergraduate working at NYU did. We couldn't find where to do it from, so we did it on my roof. This is the view from my roof, okay? This is the physics department at NYU is over here. This is Washington Square Park. The UV we're going to get from here. That's where the sun is going to come up. The dirt, we actually use dirt in this experiment for a reason I'll tell you in a second. The dirt is from the park, okay? And the cold is from New York winters. This was a very cold winter, so it was a good winter for doing this experiment. So the apparatus here set up on a chair on my roof looks like the following. Very sophisticated apparatus, okay? It's a styrofoam box, okay? There's dirt in it, and there's a saran wrap cover on it. And over here, there's a piece of aluminum foil, okay? And you put the samples in there. There's the sample. Now, what happens is, at night it gets cold, that's clear. In the morning, the sun comes up over the horizon over here, over this styrofoam container, and it shines on the sample. And after 26 degrees, which is about 2 hours or so, we want it to turn off because we don't want the light to be on as it warms up, okay? Now, I was really worried because I was thinking, when we actually do the experiment in the lab, the temperature swing we use, it's not clear we need this much, but the temperature swing we use is from 4 degrees to 45 degrees C. So I thought, well, geez, we're going to have to go to the Mojave Desert in winter or go to an ice field or something like that to do it. But then one of my students said, well, that's kind of stupid. If you wear clothing, okay, when the sun shines on you, you get much hotter than the atmosphere, right? And if you have dirt on the ground, the dirt gets much hotter than the air temperature. So just use dirt. So I did an experiment, okay, where I took this styrofoam box and I put a thermometer in it and I buried it in dirt and I left it out in the sun, and the outside temperature was 20, well, this is, I should have to convert to centigrade. The outside temperature was -8 or something like that, okay? And when the box was when it was fully exposed to afternoon sun, it was 65 degrees, right? Just under the dirt, right? So dirt works great. It actually heats up, okay? So we use dirt. And the way we arranged it is the dirt is at an angle here, so the sun is above exposing that before the sun hits the dirt, right? And then the dirt heats up, right? And then it stays hot for a day, and then it cools down at night. And that's the idea of it. Here's the dirt getting hot and stuff like that. The dirt, in our case, went to maybe 35 in this case. And all we did is we did it. This doesn't even have the date on it, does it? Rats. No, it doesn't. Rats. So I don't have the date. In any event, it worked. It worked for, we actually took the seeds and doubled them in that, and if we didn't expose it to the sun, so next to it we had a similar container where it never saw the sun, that didn't double at all. All we had was the seeds. This, right. But it doubled when we exposed it to the sun in this case. The dimers doubled. That's all it says. And then we ran out of sample, okay? So we're making new samples now. So I have to, people in New York are going to hate me for this, but I'm hoping that it stays cold in New York for another 2 weeks so we can finish this. Okay, so I've run over, sorry. That's sort of it. One other thing is, if we're going to build stuff from DNA, you might ask, can we build stuff out of DNA if we're going to do self-replication, stuff like that? Suppose I want to make a building or something. Is there enough DNA to do it? So I calculated once the amount of DNA there is in the world, our world. That's the only place we know that there's DNA so far, is our world. Our world, if you collected all the DNA, it would fill a cube that's 2 kilometers on a side. That's a lot of DNA. That's enough, for example, if you build a city just out of DNA, you could use this to build 200 cities the size of New York. So you could use it for construction material. And it's edible, so you can eat it afterwards. Okay, so that's where I want to end, I guess. And I've told you everything here. We've got evolution working. I thought that would be next. Oh, one of the things we want to do is, because a lot of people think we're cheating because we're using DNA, because we're not replicating with DNA, we're replicating using DNA, but one of the next steps we're going to do is we're going to do this with no DNA. Right? And that will use something that William was involved in, which is particles that recognize one another by shape. Okay, and this is from the Keck Foundation, the Moore Foundation, and DOE. And this is what I want to make. And probably what I'll end up with is this. Okay, thanks. What kind of device can I? What you want to make it useful for something? Okay, no, but you got to realize, if we're using the origamis, there are lots of things we could do with it. We could wire networks, we could make photonics, and we could evolve them to have better properties. So, for example, a simple thing to do is just put a gold particle on one and a dye on another one, right? And maybe have different dyes and stuff like that, and then expose them to certain light, or require them to have certain transmission properties, or require them to reflect light in a certain direction, and select for that, right? And we could do that. You'd have to think about it. The example I just gave you is not a real one, but you know, you could think about things like that, right? You can evolve them for certain things. There are also disastrous things you could imagine doing with them also. Like for instance, people don't like the idea that, you know, we're supplying this with DNA. You think that you just want to feed things, and we're feeding these guys as DNA. So it occurred, you know, we couldn't make these, so they seek out sources for DNA, and they kill it, and they take its DNA. And that probably is not a good thing to do, right? Because it'll come after us, right? But you can imagine lots of things with it that aren't just things involving DNA. The fact that you can take the origamis and attach whatever you want to them makes it very, very powerful for doing things, right? Well, you're right, but this system was designed so we could do studies. We can make it evolve as quickly or as slowly as we want, because the only thing that's determining whether a particular tile goes there is the DNA sequence. And we can make one difference, right? And that will mean that, you know, there's 65% chance of this guy and 45%, 35% of the other guy coming down, right? And exactly, it's too good at the moment, but you'd rather have something that's too good to start, right? You don't want to build in from day one that it makes lots of mistakes. No, but you don't. What I mean, for instance, if I make it so the system self-evolves, which I can do, I can put up lots of different tiles with lots of different DNA sticky ends on them, which are slightly different, right? Then the system is going to try everything. And it's going to try everything, and the one that replicates best of its own thing. What? What we did is selective pressure. That's what we did to demonstrate what it would do. But it can have its own pressure. I mean, the only thing it wants to do is replicate faster than anything else in the system. Right? Do you have something?
So are the colloids going to work, or because you talked about the colloids and then you switched?
The colloids will work, but I don't know when, because this is going really fast now. There's just too much stuff to do with this now, right? The first thing we're going to do is make it longer. There are theories about origin of life that say it's illegal to do origin of life this way, because as you try and increase the information in the chain, it becomes exponentially harder. And in order to combat that, you have to have an exponentially growing advantage. And so there are all sorts of stuff like that we want to check. But we do want to do it with colloids, and we also want to do it with colloids with no DNA. And that's one thing that we're working on actively.
And if you have a complicated 3D structure, can you replicate that, or does this only work for a simple geometry?
So the answer is this particular way of doing it is only for 1 or 2 dimensional seeds, right? But as you know, you can take anything that you can make linear and fold it into any shape you want. And that's the way biology works. So we may steal that from biology, right? It's actually much easier doing 2D than anything else for the self-replication. Okay.
Continue the question about the topic, right?
Great.